Team Interplanetar has been representing Bangladesh in different Mars rover competitions around the world since 2011. We started our journey with ERC with our Mongol E version 2.0 rover. Since then, Team Interplanetar has participated in many rover competitions around the world, such as the University Rover Challenge, European Rover Challenge, and International Rover Design Challenge. We achieved 8th position in ERC On-Site 2022, 4th position in ERC Remote 2022, and 8th position in ERC Remote 2025.
Our team's workspace is based in the university's project lab, which serves as the main center for meetings, collaboration, and rover development. Each subteam has its own dedicated area, allowing design, testing, and assembly work to happen in parallel. This is where we refine concepts, build and test subsystems, assemble the rover, and use our 3D printer to manufacture custom parts in-house. We also make use of university workshops for laser cutting, bending, and other fabrication tasks. For system validation and field trials, we use both the project lab and the open spaces across campus.
The rover features a rocker bogie suspension with bar differential and 4 BLDC motors. We have repurposed hoverboard BLDC motors for the steering system. For tires, we 3D printed TPU-based custom tires. As per ARC requirements, the rover has a system for autonomous missions that allows dropping specific objects at position. The suspension system allows the rover to traverse through harsh environment. It can climb over rocks and uneven sandy grounds.
The rover arm has 5 degrees of freedom and is manufactured using stainless steel. The wrist was manufactured using aluminum and 3D printed lightweight materials. The end effector features 3D printed claws with inbuilt laser for precise guidance. It also has a dedicated servo-controlled poker mechanism. With the aid of an onboard camera, the end effector can push buttons, flip switches, plug in USB, and can type on keyboards.
We have a new BLDC hub motors driven by two O-drive boards using closed-loop field-oriented control. Running on a 36-volt rail, integrated Hall sensors provide live odometry and tunable torque control through the Jetson Oil Nano for precise navigation. Our custom ARM board uses an ESP32S3 to manage 6 joints. BTS drivers control the high torque actuators while DC motor controllers drive the wrist and gripper. Potentiometers and servos provide real-time angle feedback. The centralized PDB replaces mechanical relays with MOSFET-based switching for better heat management. It steps down 40-volt input into regulated 36-volt, 24-volt, 12-volt, and 5-volt rails. While an Arduino Nano monitors the rail, shows live telemetry on an onboard OLED, and enables software-based subsystem isolation.
We have moved to a third gen 40-volt power supply using industrial grade 5S3P battery pack. Built with high-star 1865 cell, these include internal BMS protection and are fully hot shippable, ensuring zero downtime during critical mission phases. The science board controls the auger drill, linear actuator, and sample containers using HX711 amplifier for soil mass measurement and moisture core for in situ data. A dedicated auxiliary board manages the pan tilt antenna camera, laser targeting, and solenoid drive and keyboard poker. For safety, an external hardware kill switch instantly cut power to the wheels, arm, and drill, while a software kill switch allows the control station to selectively disable individual PDB rails, providing both rapid shutdown and precise fault isolation.
For ARC 2026, we have designed a compact yet powerful science module. The science module is 36 cm long and 26 cm width. A lightweight aluminum frame minimizes overall weight, while high-strength stainless steel is used in critical guides and moving parts, ensuring smooth operation. To achieve the science mission, 4 functions are performed consequently. These are drilling, sample collection, storing samples, analyzing the samples.
We have an auger drilling mechanism capable of extracting soil from the depths of 15 cm and storing it in 2 airtight containers. Rack and pinion mechanism is used to store the soil inside the containers and avoid any type of contamination. The weight of the soil is measured using load cells placed under the containers. For onboard testing, the soil will be collected from the drill and mixed with water in a container. Then the sample will be transferred to 4 test tubes containing chemicals using a pump where color changing will be observed.
For laboratory tests, we have used color changing chemical analysis for the detection of organic materials. to determine the absence or presence of life. Iron from phyllosilicates have been used for justifying our hypothesis. Rock sample analysis will be conducted with the help of a Pi 2 camera. Habitability analysis will be done with the help of temperature, pH, and NPK sensors.
The rover's base station provides wireless communication, manual teleoperation, and remote monitoring through a custom Linux-based interface. Operators can arm or disarm the rover, control wheels and arm joints, and monitor map position, camera feed, sensor data, and latency. Wireless communication is supported by a sector antenna on an antenna stand. For science, night, and collaboration missions, we use a dual-link communication setup for reliability. The Ubiquiti Rocket M2 provides the high-bandwidth ROS2 network for telemetry, video, and data transfer, while the CV UniRC offers a dedicated RF link for manual control up to 40 kilometers and stable 1080p video streaming. All systems comply with Turkish law number 5809 for safe field operation. At the core of our rover is a distributed ROS2 ecosystem powered by Cyclone DDS for fast, reliable communication. High-level perception and autonomy run on NVIDIA Jetson units, while distributed ESP32 microcontrollers handle low-level hardware control. This separation keeps wheel and arm control stable and responsive even during demanding tasks like real-time mapping and navigation. Our custom-built GUI serves as the main operator interface using UDP for low-latency robotic arm control and WebSockets for differential drive command. It provides real-time O-drive telemetry including bus voltage, current, position feedback, and network diagnostics, allowing operator to monitor system health and prevent failures during operation. This year, our autonomy stack is built on NAV2 framework for reliable localization over unstructured terrain. Localization combines wheel odometry, Z visual inertial odometry, and GNSS data through an extended Kalman filter to provide accurate real-time positioning for GPS waypoint following and obstacle avoidance. The rover executes a custom spiral search pattern to detect Oruko markers, while a behavior tree manages every stage from localization and navigation to search and recovery for smooth mission flow. In autonomous mode, the rover runs without human intervention, receiving RSCP commands.
For perception, the Z2i camera's point cloud is used to find the highest point for deployment of antenna. OpenCV detects Haruko markers for mission transitions, while depth camera, wheel odometry, and IMU data support navigation inside the lava tube. At Shackleton Crater, a custom-trained YOLO V26 model detects basalt rocks by identifying dark texture and color, then sends the coordinates via RSCP.
An addressable RGB LED strip provides rover status feedback, green for manual mode, yellow for autonomous mode, and red for disarm state, with a 5-second activation delay before motion for safety. The ROS2 system continuously monitors the communication health and automatically disarms the rover if the link drops below a safe threshold. Operators can also trigger a remote emergency stop through the GUI for immediate intervention.
For the collaboration missions this year, our astronaut will be trained to assemble the rover from scratch within a limited time. They will also be trained to set up a communication system to establish a stable link with the ground station and confirm that the rover is ready before the mission starts. We are thankful to our sponsors and partners for their continuous support. Thank you for watching. See you in ARC.